Hello and welcome to this section of the chemistry tutor. I'm actually very excited to teach this lesson because really it's the culmination of everything we've learned in redox reactions up until this point. And that is the topic of how do you balance these redox reactions when they're in an acidic solution. I'll talk about the acidic solution part in just a second, but suffice to say that up until now you've seen that redox reactions, because of all the ions and the electrons floating around, can be difficult to balance, and it's difficult to just look at it and figure it out. So there's this process, and we kind of learned the skeleton of this process for a few very simple problems just recently in the last couple of sections. But you need to realize that when you are doing these redox reactions, they're a lot of times happening in an aqueous solution, and a lot of times they're happening in an acidic solution or sometimes in a basic solution. I mean, when you think about all the chemistry happening in your body right now, there's millions of chemical reactions happening inside your body right now, and they're all happening in a water solution. And if you think about what an acid is, if you remember back to all of our previous lessons about what an acid is just a water solution that has extra hydrogen ions, H+ ions floating around. And it turns out that in your body and in lots of chemical reactions in real life, these reactions are happening in a solution, in an aqueous solution, but that has some of these extra hydrogen ions, so they're kind of an acidic solution. Sometimes they'll have hydroxide ions, which are basic solutions. So when you're looking at these redox reactions that are happening in water, a lot of times they're happening in acidic solutions, sometimes they're happening in basic solutions. And what you need to realize is that it encompasses a huge class of things. So because you have these extra hydrogen ions floating around, because you have water in there, and because the chemical reactions themselves get more complicated, the process for balancing them can be a little bit tricky or challenging at first. All right? So the title of this section is Balancing Redox Reactions in Acidic Solution, Part 1. So in your book, or in your test, it might say, balance this redox reaction, the solution is acidic. If it says it's acidic, then you need to apply these rules. If it says it's a basic solution, I'm going to show you how to do that a little bit later. It's not very hard. And then if it doesn't say anything at all, then you probably should assume it's neutral solution, which the acidic rules that we're doing here kind of cover that as well. So let me give you the process on how to do it with a acidic solution, and then I'll show you how to handle the other cases with other problems later on. So there's a lot of steps, so what we're going to do is work and show you every single step here, and then this is something that you'll need to remember to solve all of the future problems. Okay, so this is for the procedure for balancing a redox reaction, procedure for an acidic solution. And again, on your test, it'll tell you this reaction's happening in acidic solution, balance it, and then you'll need to use this method. All right, so the reaction is, let me switch colors over here. The reaction is Cr2O7. This is an ion that has -2. This is called a dichromate ion, plus iron with a charge of +2. And it gives us chromium 3+ plus iron also 3+. So this reaction, as with all of these redox reactions, they look very simple. You know, they look like they're not a big deal because you see you have, first of all, this is iron over here, so I'm going to put it Fe here. Well, you can look at this and you can say, well, as far as atoms go, I've got one atom of iron, no big deal. Then I've got one chromium and I've got two chromiums over here. All right, so since I have two chromiums, I can just put a 2 there. This is what you would do if you didn't know anything about redox. So I can balance the chromiums and the irons easy, but then I have this oxygen that's there, okay? And there's no oxygen on the right-hand side of this equal sign, so what do I do? And also, what do I do about the electron transfer? And also, you can't just balance these redox by just looking at the atoms because clearly there's electron transfer going on between this stage and this stage because the ions are different, charges are different. So you have to look at all those things. You've got to look at the electron transfer, you've got to look at the number of atoms on both sides, and then in this case, when you have more complicated reactions and have oxygen and hydrogen, what do I even do? I don't even have any oxygen on the right-hand side. But what you need to realize is that these reactions are happening in aqueous solution, which is water solution. Water is H2O, okay? And then since it's acidic, I have extra hydrogen ions, H+, floating around. So I can use, and in fact what we do is we use these hydrogen ions and these oxygens that are in the water to balance the reaction. So let me take you on a journey through the step-by-step process. It'll look a little daunting at first, but once you work 5 or 6 of these things, it'll become like clockwork. So here is the reaction. What we need to do is step 1. Step 1, when you're given a redox reaction like this, an acidic solution, you need to write it as a net ionic equation. A net ionic equation is actually what we already have up here, but I just want to write it as step 1 so that you make sure and see that. In this case, you can figure out if it's net ionic because you have the ions already written there. They're already kind of telling you that these things are happening in aqueous solutions, and the ions are already dissociated and broken down. I mean, you don't just go off the shelf and buy iron ions and shake them out of a bottle. It's going to be some iron compound that you buy, and you put it in the water or your acidic solution, and it dissociates, and those iron ions are then going on. So what you have when you have net ionic equations is you write the full equation out, and then you cancel all those spectator ions because they're not participating, and what you have left, which is in this case what we have on the board, is the net ionic equation. It's basically everything left over that's actually participating in the reaction. So we've covered net ionic equations before in previous sections. Make sure you understand what that concept is. Most of the time in your book, you will already be given a net ionic equation to balance. So most of the time that's okay, but if you don't have that, then you might need to go and write the net ionic equation first. So that's step 1. So I'm going to put a check mark here because this is basically already done. Step 1 for this particular problem is already done. In most problems, they will probably be given to you like that. All right, so step 2. Write half reactions. Write half reactions. Okay, so what we need to do is look at what we have. We have a chromium or a dichromate ion, and then we have that going to chromium ion here. So let's write that down. So we have Cr2O7 charge -2. It's going to Cr3+. Now in this procedure, when I tell you to write the half reactions, I'm not talking about the electrons yet. I know that in all previous half reactions we've been writing all the electrons transfers. But you'll see in a minute that because we have other things going on here, it's going to be tough for you to write the electrons at this stage. So right now, when I say write the half reactions, all I mean is identify the things that go together. This is going together. These guys here are going together. So these are the 2 half reactions. So let's write iron 2+ going to iron 3+. So these, for the purpose of this procedure, are the half reactions. It hasn't encompassed any electron transfer, but those are the half reactions. We're writing it down into every little tiny step. So step 3. All right, we're going to balance atoms other than hydrogen and oxygen. So in other words, in the half reactions that we have written down, we're going to balance them, but we're only going to balance the items that are not hydrogen and not oxygen. The reason is because if you start dealing with hydrogen and oxygen too early, then you go in a circular loop and it gets hard to balance the thing. So you do everything else first, then we deal with the hydrogens and oxygens later, and you'll see why in a minute. So what we do is I rewrite what I have here. I have Cr2O7 giving me Cr3+. Here I have iron 2+, giving me iron 3+. And then I look and I try to balance these things, and I look here, I'm balancing atoms other than hydrogen and oxygen. So here I have 2 chromium atoms. So I'm going to put the arrow and I'm going to put a 2 here. So I've balanced the 2 chromiums with the 2 chromiums. The 1 iron is already balanced with the 1 iron. We're not looking at charges. We're not looking at this oxygen because it says we're balancing things other than oxygen and hydrogen. All we're doing is writing our half reaction down and balancing everything other than hydrogen and oxygen. Okay? So let me move over to the other board over here. Actually, I'm going to continue to do it right here. I think it'll be a little clearer if I just write it right underneath. So step 4. Okay? Now what we're going to do is balance oxygen by adding H2O. So what we're going to do is we're going to freely add oxygen to these half reactions in order to balance the we're going to freely add water to both sides of whatever we need to, or to whatever side we need to balance oxygen. So let me go ahead and do it, and then I know it looks a little weird, but then I'll be able to show you clearly why it works and why it's important. So let's look at the first half reaction. We have Cr2O7, and this is giving us 2 chromium ions. See, we've balanced the chromiums. Now it's telling us to balance the oxygens by adding water. So here we have 7 oxygen atoms. So the way that you do that is you add 7 waters. The reason you add 7 of them is because it's H2O, so there's 1 oxygen here. So when I add 7 waters, I'm adding 7 oxygen atoms to balance the 7 oxygen atoms here. Now you might ask yourself, how can he just add water anywhere he wants to balance whatever? The reason we can do that is because this reaction is happening in water. Okay, so water, believe it or not, is sort of a participant, at least in some way, in what's going on here, right? So, I mean, this oxygen just doesn't disappear from the face of the earth. Something happens, all right? So some of the water is involved. So I can freely, at this step, step 4, I can freely add water anywhere I need to balance the oxygen, okay? Now, for the next half reaction, I'm going to write it down again. Now notice there's no oxygens here, so I don't need to add any water. So this is already basically balanced, but I needed to add it at this step. Now notice that there's a little tiny problem that cropped up. See, I've balanced the chromiums already, and I've balanced the oxygens already. But because I added this water here, I've added 14 hydrogens to this side. 14 hydrogens. And you know that you can't do that. You can't just have hydrogens, sitting around that are not balanced. So in the next step, we're going to take care of that problem. So let me go ahead and write down step 5. All right, step 5. I'm going to balance hydrogen by adding hydrogen ions. Now, if you remember, we said at the beginning of the section that this was occurring in an acidic solution. All right, in an acidic solution. Because of that, in this water, there's hydrogen ions, extra ones floating around. That's what an acid is. We've talked about acids in great detail. Acids have hydrogen ions floating around. The more hydrogen ions floating around, the stronger the acid you have, right? So super strong acid has lots of hydrogen ions. But the point is they're freely sitting around. So because we introduce these extra hydrogens here, we're going to add some hydrogen ions to the other side to balance. And if we do that, how many hydrogen ions do you think we need to add? Well, 7 times 2 is 14, so we'll need to add 14 hydrogen ions to the other side to pull this off. So that's what we do exactly. So you literally write it as 14 hydrogen ions. You have to put the plus sign there because these are ions. Cr2O7 negative 2 gives us 2 chromium 3 plus 7 H2O. So this is what we've done here. The reaction under it is really unaffected. Fe2 plus yields Fe3 plus. We don't have to do anything here because there's no hydrogen. Step 5 is balance the hydrogens by adding hydrogen ions. We added 14 over here, so we have to add enough to cover it, to balance however many hydrogens we have on this side. So that's step 5. I know it's a little bit crazy, but we're actually making progress. We're over halfway done with this procedure. All right, so here we have step 6. Step 6, balance the charge by adding electrons. Now, before, when we did the half reactions, we just kind of added the electrons in there because we could just see how many electrons we needed. But in more complicated reactions, like I'll give you an example, this one here, this iron, it goes from 2 to 3. So we know there's only 1 electron that's involved there, right? That's pretty easy to write that one down. But what happens here? We have 14 hydrogen ions that are positive, and then we have 1 of these dichromate ions that are negative, and then over here we have this. So how many electrons do I need to add, and where do I need to add them in order to pull it off? Well, in this step, when it says balance the charge by adding electrons, here's what you do. The first thing you do is you rewrite your reaction. I know it's a pain to rewrite these reactions over and over again, but I think it's going to make your life easier in the long run. So here's what I do. I'll just tell you straight up what I do. I rewrite the reaction, and I'm not kidding around. I actually do this every single time, even though, you know, I kind of know what I'm doing, but I do this every single time. I rewrite the reaction, and what you do is you look on the left-hand side, draw a little curly bracket, and to remind yourself you're looking at this. What you want to do is add up the total charge on one side of the equation. So here you have 14 hydrogen ions. Each of them are +1. And you have 1 dichromate ion. Each one is -2. So really you have 14 positives, and then you have -2. So you have 14 minus 2 equals, here you have +12. So if you look at the charge on the left-hand side of this equation, this whole thing, the total net charge of everything here is +12. And then you look at the other side, everything, including all this stuff, and what do you have here? You have 2 times 3, you have +6. You have +6. See, the water has no charges, so it doesn't participate. 2 times +3 is +6. So what you do is you sum up all the charges on one side, and you sum up all the charges on the other side. And they're going to be different because there's electron transfer going on. And what you need to do is you add electrons to whatever side of the reaction is needed in order to balance that charge transfer. All right, to balance that charge transfer. So what I'm going to do is rewrite this equation in green. And what I know is that since I've got 12 over here and I've got 6 over here, I need to add 6 electrons here, because 6 electrons will pull down this charge and make it equal to the 6 on the right. So 6 electrons plus 14 hydrogen ions plus Cr2O7 to -2 chromium plus 7H2O. So you see what I've done is I've taken this half reaction and I've calculated the charge on both sides, and I've added 6 electrons here because I'm trying to make this +12. I'm trying to make the two charges equal. And I can only add electrons, so I have to add it to the most positive side. But if I add 6 of them, then the sum total of the charges over here will now be 6, and that will match the 6 I have over here. So this reaction is very important because it's basically done with regard to that. Now, when I look at the other half reaction, see, I have another half reaction to deal with here. This is going to be Fe2 plus, and then we have Fe3 plus. So where does the electron go here? See, this one particular one's a lot simpler to look at. Where is this going to go? I need to have an electron, one single electron on this side. See, if they're simple like this, where you just have one ion going to another ion, it's very easy. I know that there has to be an electron there. I know that there has to be an electron here because I have a positive ion, that's +2, and it's going more positive. The only way that can happen is if I lose an extra electron. So what you do when it's very simple is you can just write the electron wherever it makes sense. In the more complicated ones, like all of this, it would be impossible. You sum the charges up and then you add the electrons in the right place. I mean, another way to look at it, if you really want to, if you wanted to do it this way, what's the total charge on this side? +2. What's the total charge on this side? +3. Okay, so +2 +3, where does the electron go? The electron has to go on this side to bring this down and make it match with the other side. So either way you want to think about it is fine, but at this stage, in step 6, balancing the charge by adding the electrons, you need to balance charge on both sides of these reactions, on both sides of the equal sign. So we're done. The green equations are the final part of that step. Now what we do is step 7. Multiply to balance the electron gain loss. Because at this step here, I have correctly balanced the charge on the left and on the right hand side as far as each individual half reaction, but the reaction as a whole, in this case, I have 6 electrons over here, and I have 1 electron over here. So you remember back to the last section with a simpler problem we said, well, we get down to this step, we're losing a different amount of electrons than we're gaining. So we're following the procedure to the letter, but now we have 6 electrons over here on one side and 1 on the other. That's not going to work. So what we need to do is multiply however we need to make this work. And notice that we have 6 here and 1 here, so all we really need to do is multiply this reaction by 6, because then I'll have 6 electrons lost over here and 6 electrons gained over here. So in order to make this consistent and beautiful and everything else, I'm going to rewrite the top equation because there's no changes to it. I don't have to multiply anything. 6 electrons, I don't have to multiply anything to that one. 14 hydrogen ions, Cr2O7, yields 2 chromiums and 7 H2Os. All right, so that's that. And then what I'm going to do here is take this reaction, I'm going to draw a little arrow, and I'm going to multiply by 6. I'm going to multiply this equation by 6. So I'm going to multiply this by 6. I'm going to have 6 Fe2 plus yields 6 Fe3 plus 6 electrons. 6 electrons. All right. So at this point in the game, I should have 2 half reactions with lots of other stuff added to it. But the most important thing that I'm getting to is the electrons that are gained on one side must be equal to the number of electrons that are lost on the other side. All right, so we've multiplied to balance the electron gain and loss. There's one more thing to do in step number 7. After we multiply, we're going to go ahead and put it in there, and that's going to be add the reactions. Okay, so when we do step 7, we multiply to balance the electrons, and then we also add the reactions, and that's very convenient because we do it right on top of one another. So I'm going to draw a line here, okay, and I'm going to put a plus sign here, and then underneath we will write down the addition of both of these reactions. So we look at everything on the left-hand side, and that will be 6 electrons plus 14 hydrogen ions plus Cr2O7 to negative like this, plus 6 Fe2 plus. And on the right-hand side, we'll have 2 chromiums plus 7 waters, and we have 6 irons, 6 Fe3 plus, and then we have 6 electrons. Okay, make sure you understand that. All we do is we take everything on the left, add it together, everything on the right, add it together. And notice that we should have the same number of electrons on the left and on the right, just like we've been doing in the last couple of problems. So now, we're almost done. Step number 8 is the final step. Step 8. And that is to cancel anything common to both sides. Okay, so we're going to cancel everything. Now I'm not going to mark this up too much here, but I do want to point out that we have 6 electrons here and 6 electrons here, but there's really nothing else common because I have 14 hydrogen ions. I don't have any hydrogen ions over here. I have one of these dichromate ions, but I don't have any of those over there, so I can't cancel those. I have 6 iron ions with a charge of +2. I do have 6 iron ions, but this is a charge of +3, so these are different ions, so these are not the same. So the only thing in this particular problem that you can cancel is the 6 electrons. So if you write it all down and get it all, you know, into a final answer, what you're going to have is 6 Fe2 plus 14 hydrogen ions plus Cr2O7, charge of -2, 6 Fe3 plus 2 chromium 3 plus 7 H2O. So let's double check everything. We have 6 irons with a charge of +2 on this side. We have 14 hydrogen ions. We have 1 dichromate ion, and then we have the 6 electrons have canceled, so they're gone. And then on the other side, we have 2 chromate ions +3, and then we have 7 waters, and we have 6 irons with a charge of +3. So this is all correct. So this is the balanced chemical reaction for this redox. Now this looks crazy, I know it's a long process, but really once we get through, bang through a bunch of them, I don't have to write all these steps down all the time, you will get the hang of it. So notice there's no way that you could come up with this just by looking at this problem. I just don't believe it. If you can do that, then you're going to do very well in life, okay? Because we had to add some waters here, we had to add some hydrogen ions here, you know, and plus the coefficients are not really easy to come up with either. It's a far cry from what we started with over here, which is this one. So it looked very simple. It looked like the ions were already balanced, and it looked like it was a very simple change to make this guy with a number 2. Maybe there's some oxygen, I don't understand, but it looked like it was going to be simple. Let me go through the procedure again, just to make sure you understand it. First, we write it as a net ionic equation. That's already done. Then we write the half reactions, not with the electrons, but we just write the ions on the left and the right-hand side that go together. Then we balance the atoms that are not hydrogen and oxygen. So we put a 2 here to balance this chromate. We didn't have to do anything here. Then we balance the oxygen by adding water. We can do this because this is happening in an acidic solution of water. So because we had 7 of them, we added 7 waters over there. We didn't have to do anything to this. Step 5 is we balance the hydrogen by adding hydrogen ions. The reason we add the hydrogen ions is because this is an acidic solution that has tons of extra hydrogen ions floating around to help with this reaction. So because we have 14 hydrogens here, we had to add 14 hydrogen ions on this side. We didn't have to do anything here. Next, we balance the charge on both sides of the equal sign by adding electrons. This is very similar to before when we were adding the electrons to the half reactions. It's just that now with more complicated reactions, you have to do this summation process to figure out how many electrons to add. Because in these simple things, like in these simple ones, yeah, you can figure out that there's 1 electron in there that's going to be required. But here, with all these ions, how many do you need? So what you do is you add up the charge on both sides. Here you have 14 minus 2, you had positive 12 over here. Here, 2 times 3 gives you 6. So you have to take into account the numbers that are in there. So you have positive 6. So you have 12 and 6, and then I can add electrons to one side. So I add 6 electrons over here to bring this charge of the left-hand side into balance with what we have on the right-hand side. And we did the same thing with the second half reaction. It's just so much simpler. We know that there has to be 1 electron here because there's just the 1 ion. Step 7 is we multiply however we need to multiply to balance the electrons gained and lost. So here we have 6 electrons over here and we have 3 over here. So we just choose to multiply the second equation by 6. The top equation stayed exactly the same. Second equation multiplied by 6. Now we have 6 electrons on both sides. Part of step 7 is to add these reactions. So we write down everything on the left, we'll write down everything on the right, and then the very final step is to cancel what we need to cancel. The only thing we can cancel is the electrons. In the end of the day, when you write this down, you should always have your electrons canceled. There should not be any electrons left over here. Now, let's check this and see if it's right, because it sure would be nice if we could figure out if it's correct, right? The first thing you do, or the first thing you need to realize, is that you need to balance for charge and atoms. So let's check the atoms first. We have 6 irons. We have 6 irons. We have 14 hydrogens. We have 14 hydrogens. We have 2 chromates. We have 2 chromates. We have 7 oxygens. We have 7 oxygens. So far that's great. The next thing we need to check is, do the charges balance on both sides of the equation, of the chemical reaction? So the way you do that is you have to add up the charge of the left and on the right. Here, 2 times 6 is positive 12. Here is positive 14, 14 times 1. Okay? Here is just 1 ion with a charge of negative 2. So here I have 12 plus, this is going to be 12, so here I'm going to have plus 24. That's the total charge on the left-hand side of this chemical reaction. Now let's go over here. 6 times 3 is 18. 2 times 3 is 6. And when you add these things together, you're going to get positive 24. So you have a number of, as far as charge goes, of positive 24. Here you have positive 24. You've balanced the atoms on both sides, and you've verified that the charge is balanced on both sides. If once you're done with your problem, if you verify that both of those things are true, then you've balanced your chemical reaction. A couple other things I want to talk about really quickly. The very last step talks about canceling anything common to both sides. Here we canceled electrons. Here I have 7 waters. If I had some water over here, because it might turn out that I have to add water to the other side, you'll see as we do more problems. If I have some extra water over here, I can cancel as many waters as I can that are common to both sides, much like an algebra equation. The other thing I want to point out is one gotcha that gets a lot of students that will just screw you up early on is when you get to this step, it says write the half reactions, and then it says balance them to balance atoms other than hydrogen and oxygen. A lot of students forget this step. They write the half reactions and they jump down here. You need to balance this stuff other than hydrogen and oxygen, or you're not going to get the right answer. So this is the procedure. What I'm going to do now is erase this board, and I'm going to write the procedure as step 1, 2, 3, 4, 5, 6, 7, 8 really quickly so we have it as a reference. So when we work our extra problems, our other problems, we will have it available. So I'm going to erase the board now, write the steps down so they're ready to rock and roll for our next problem. All right, now what I've done is I've erased the board and I've written down our 8-step procedure for balancing redox reactions in acidic solution, but without all of the work that we did for that one problem. So it's important to, if I just write this down, it doesn't make sense to you, but we worked the problem, I think you understand it. Now here's something I'm going to leave on the board and something that you're going to need to end up remembering. First thing, write the equation as a net ionic equation. Most of the time this will already be done. And then you divide it into 2 half reactions just with the different ions on both sides. Then you balance the atoms other than hydrogen and oxygen. Then you can balance the oxygens by adding water anywhere left or right hand side to do that. Then you balance the hydrogens by adding hydrogen ions, as many as you need on both sides. Then you have to balance the net charge. You have to calculate the charge on the left and on the right hand side and then add electrons wherever they're needed to bring the charge into balance on both sides of both of these half reactions. Then you need to balance the electron gain loss. If you have 2 on one half reaction and 5 on the other, you're going to have to multiply somewhere to balance the gain and loss on both of those half reactions. Then you add the half reactions together. Once they're added together, you're going to have some commonality of something on the both sides, so you'll cancel anything common to both sides of that reaction. That is the procedure. I know it's a pain, but to be honest with you, when I learned it, I was flat out confused the very first time I learned this many, many years ago. I didn't have a bulletproof procedure like this. I didn't have a lot of examples worked for me. I didn't have a lot of practice, so it just seems daunting. You get confused. But I promise you, as we work more of these, I'm going to leave this list up here, so that as we work them, you'll start to remember, okay, I got to do that, I got to do that, I got to do that. And so as you get practice, you will remember it without having to actually memorize it. So make sure you understand this section. Make sure that you can solve this problem yourself, so go ahead and try that now. And then follow me on to the next section. We're going to work a lot of these balancing type of problems because it really is the core of this part of chemistry. And once we can do that, then we can move into other topics and redox reactions and help you gain confidence and experience. So I'm Jason with MathTutorDVD.com. I hope you've enjoyed this. Make sure you understand it. Follow me on to the next section where we will continue working with redox reactions and balancing.